Okay, hello everyone. I'm Harvey Miller, Director of the Center for Urban and Regional Analysis, and welcome to the second of 3 Spring 2018 events on cities and water in the area of climate change. And I want to thank our co-sponsors, the Ohio State Office of Energy and Environment and the Mid-Ohio Regional Planning Commission. Be sure to attend our third event, which will be Tuesday, April 17th at a different time from 3 to 4 p.m. in Derby Hall 1080. We'll be having William Hunt, who's the William Neal Reynolds Distinguished University Professor at North Carolina State. And he'll be talking about green infrastructure and ecosystem services, the future of stormwater management. As you've noticed from the last few days of walking around Columbus, we have an issue with stormwater management in the city, especially in my neighborhood where there seems to be standing water everywhere. So this is an issue which I think is very near and dear and important to our future here under climate change in the city of Columbus. Just for those of you who are thirsty, we're not bringing plastic bottles anymore to our events. We'll be having lunch, so if you're just remember that for future events, please bring your own bottles. We're trying to battle the epidemic of plastic in the world, so hope you understand that. So information about CURA can be found at cura.osu.edu. You can also like us on Facebook, follow us on Twitter. We're not on Instagram yet. I guess we'll work on that a little bit later. Also, today's event offers a professional development hour. Is that right, PDH? Did I get that right? A PDH offered through the Ohio Water Resources Center. And they can mail you a certificate if you're a practicing engineer. There's a sign-up sheet in the back. Please provide your email, and you'll get credit for one PDH for attending today's talk. And I'm pleased to introduce Christopher Impellitteri. He is the Associate National Program Director of the EPA's Safe and Sustainable Water Resources Program. He leads the EPA's Green Infrastructure and Water Systems Initiative, which serves to improve and protect the nation's water infrastructure through sustainable solutions. He has a BS in biology from Virginia Tech, an MS in geology from Old Dominion, and a PhD in civil and environmental engineering from the University of Delaware. He's a self-described academic mutt, I guess, in the combination of degrees. But mutts are often the best ones around there.
Well, thank you. My nose is cold.
His past research has focused mainly on the fate, transport, and bioavailability of contaminants in soil sediments and water. Chris has a long history in science, starting as a self-described lab rat in the pesticide residual analysis lab at Virginia Tech. He also worked on a nitrogen application field project on farms around the Chesapeake Bay, and also in between his degrees served as a Peace Corps volunteer in Burundi, East Africa, experiencing the devastating effects of malaria and gaining a better understanding of environmental costs and benefits of pesticides for mosquito control. And his EPA bio page has several fun facts about Chris. He says if he wasn't a scientist, he'd be leading a rock and roll power trio.
That's right.
Yeah. What music would you cover?
Oh, all kinds.
All kinds?
Yeah.
Okay. If he could have one superpower, it'd be bug whisperer, so he can get them all out of his house without using pesticides. If he was stranded on a desert island with other survivors, he would take on human waste management because it gets him out of every other job. And finally, he has advice for students considering a career in science: have patience and perseverance. On that note, Chris, please.
Thank you very much. I really appreciate the opportunity to talk to you all today. Can everybody hear me in the back okay, or should I mic up? Yeah. Go ahead and mic up. Okay. She said, press this until it turns green. Maybe. Speaking of this mic, is that better? Okay, good.
Yeah.
So I just drove up this morning from Cincinnati, Ohio. I work in one of the 2 big EPA Office of Research and Development labs in EPA, the Cincinnati lab, and then there's another big one in Research Triangle Park in North Carolina. And the Cincinnati lab really mainly focuses on water and land issues. Our research lab in Research Triangle Park focuses more on the arena of air. So I am responsible for leading research in the water engineering and water infrastructure talk to you a little bit today about what we've done in the past as it relates to green infrastructure, and a little bit about where we want to go. I think there's a common theme amongst not only many universities and municipalities across the country, but a lot of professional organizations like the Water Research Foundation, and it's this concept of one water. And we really can't stovepipe things as much as we have in the past. I think these changes, you're seeing that in universities, for example, but out in the real world at drinking water plants and wastewater treatment plants, often the logistics and the infrastructure and politics are completely separate between a system that has to deal with drinking water treatment and a system that has to deal with wastewater treatment. So we're trying to push these things together. In some ways, that may be a silver lining for reduced budgets. You're starting to see this coalition, I think, or this collaboration, increased collaboration between what were traditionally stovepiped in the past. So maybe that's being a little Pollyannish, but you know, I like to try to take the sunny side of the street. So in real general terms, what are some of the challenges that we have to deal with when we're talking about stormwater? Drought and extreme rainfall. I'm going to tell you right now, and I'm going to be blunt and open and honest with you, you will not hear me make or state the phrase climate change. I will probably use a euphemism such as increased precipitation or something along those lines. But this administration has made it very clear to us on how they want us to deliver these messages. So to me, it's semantics. I know some people care about it deeply. These semantics are important, but I can tell you right now, maybe I'm more on the engineering side in the sense that I don't care what you call it, you got to deal with it, right? I don't care if it's increased precipitation or climate change, whatever it is. When it comes to water management, we still have to deal with it, period. So just wanted to get that out of the way. And you're welcome to skewer me later if you have any comments about that. Another issue, a big issue, population changes. I don't know how many of you are familiar with water forecasting models, but typically in municipalities across the country, today and for many years in the past, water forecasting, water demand forecasting models are almost exclusively based on population changes and an extrapolation of that population change. Only recently and only in a few instances do you have cities starting to include issues such as changing precipitation amounts, changing temperatures, these types of things. So that's just creeping into these models in a lot of instances. Some cities have been doing this a lot longer than others, but population changes have a huge impact. And that cuts both ways, right? So many of you, I'm sure, if not everybody in this room, are familiar with what happened in Flint, Michigan a couple of years ago with lead. And our office worked quite a bit with the city of Flint to remedy that situation, and we still are working on that situation. But one of the issues there was a loss of population. So you start to have things like changing residence times and distribution systems, and that can really affect the quality of the water within that distribution system. Those are just some of the examples. And all these things contribute to stormwater management issues and water supply and treatment and delivery issues. So even though the title said that I'm going to talk about green infrastructure, and I am, I will also talk about some other things that link into green infrastructure and take this one water approach, if you will. Gray versus green. I was talking with our host before the meeting, and he told me about a cistern or a collection system that engineers put under the Scioto 5 years ago-ish. One of the big benefits of gray infrastructure, and I'm gonna just, you can read the bullets, I'm not going to read them for you, but the last bullet on there, I'll just focus on that one for a second. That pro is really important, the more controllable aspect, right? So engineers love gray infrastructure because you've got a consent order decree if you're a combined sewer system, and I'll define that in just a second for those of you who don't know what a combined sewer system is. But you've got a certain volume of water that you've got to take care of based on that consent decree. From an engineering perspective, piece of cake. You need 5 million gallons, we'll build a 5 million gallon tank, we'll stick it under a bridge, a river, or wherever. It's calculatable, it's controllable. That is one of the big challenges with green infrastructure, and something we're really working hard to try to get a better handle on. And really what it boils down to is, does it work? And I'll try to go into some of the details of what I mean by does it work in a few more slides. Some of the examples of green infrastructure that we work with now and in the past include very very small-scale green infrastructure implementation, such as rain barrels and rain gardens, up to larger scale implementation that could include permeable surfaces in larger detention areas that involve some sort of green infrastructure. So how do we get here? Land development, no matter where you are, and it could be rural, suburban, urban, doesn't really matter. If you mess around with the land, that's going to have consequences for where and when water decides to move, or how it moves, where and when it goes. That little cartoon on the right, many of you probably can't see it, but the upper left square, if you have no ground cover, you've got about 50% of the water that hits the ground, either going into deep subsurface penetration or maybe shallow subsurface penetration. This is very simplified, right? So there's going to always be geologic effects and how things are stratified, and if there's barriers to that water and how it's going to move. But once you get down into an urban setting, you may be down to around 10 to 15% of that water actually getting through the urban environment and down into the ground. So that's a big difference. Where does that water go? It typically runs off, right? So let me get back to combined sewer systems. For those of you who don't know what they are, that is where the stormwater and the municipal wastewater are combined at some point in your collection system, and it all goes to the treatment plant. Cincinnati is a great example of a CSO. I believe Columbus is a great example of a combined sewer operation. During high precipitation events, in many instances, they literally have to open up the floodgates. So in Cincinnati, where we do a lot of work in an area called Mill Creek, which a lot of that creek is no longer a natural creek, it's actually a concrete lined drainage area. If we have a high precipitation event, those gates will open because the system's overwhelmed, and that sewage goes straight into Mill Creek. And that Mill Creek discharge points, and there's several of them, there's several locations of these CSOs, or the CSO discharge points, that are just a stone's throw away from the Ohio River. So that's going into the Ohio River pretty rapidly. Right across the river in Cincinnati, Kentucky's got the same issue. Sanitation District Number 1. They are under a consent decree currently, and they're doing the best they can to try to manage these controlled sewer overflow discharge points. Also across the country, we have the short acronym is MS4, so Municipal Separate Storm Sewer System. So that's a separate dedicated collection system only for stormwater. You tend to have CSOs in older communities across the country. The Northeast, the East Coast, Upper Midwest, some areas of the Pacific Northwest are where CSOs tend to be most concentrated. And that is where most of our green infrastructure work over the past 5 to 10 years is really focused on these CSOs, but that's changing. I'll talk about that in just a minute. What are the implications? Well, as I mentioned, you get the release of this untreated water in certain instances going into our receiving waters, increased runoff from stormwater. You can have pretty severe stream erosion. I can tell you right now, the flooding a couple of weeks ago in Ohio was the worst I've ever seen since, well, it predates me. The previous flood that was even remotely close to it was 1997. But the stream bank erosion on the tributaries to the Ohio as well as the Ohio itself were pretty extreme. So there's approximately 860 communities across the United States that have pollution issues related to CSOs. 850 billion gallons estimated untreated wastewater being discharged, and that is increasing with increasing precipitation events and increasing intensity of precipitation events, and a whole slew of estimated gastrointestinal illnesses. These are just estimates. Honestly, we have no idea how many people truly get sick from these types of events. We'd love to have a better handle on that. We're working on CDC on trying to get at some of these numbers, but it's really, really hard. So there's a big difference between data when somebody checks into the hospital, where you may have better data and actually somebody following up. And it's another thing to say, I feel terrible today, I don't think I want to go to work. We just can't get a handle on what a lot of these numbers are. So that's a very broad estimate. Those numbers at the bottom, again, kind of pull these things out of thin air, right? If you go to the American Society of Civil Engineers for the past at least decade, they've been giving us a D or a D minus. Maybe one year we got a D plus on our infrastructure having to do with water and wastewater, and that hasn't changed. So we all know there's a lot of infrastructure improvements that need to be made, not only in the water arena, of course, but the transportation green infrastructure may be part of the solution. It's essentially using plant, soil, and tailored engineering techniques to essentially slow that water down to capture it. And to keep it from running straight off into the river, whether you're in a CSO or one of these separated sewer systems. Really, a lot of our research is focused at a smaller scale at EPA right now, and right now we're trying to put that together to say, and again, I'll explain this a little bit more in just a second, does it work? It is really hard, and right now I can tell you most municipalities across the country, when they are facing a consent order from the state and or the EPA region, they will use some form of model to estimate how effective that green infrastructure is going to be. And this, honestly, I'll use a non-engineering term here, it's really loosey-goosey, okay? When you get the model results, you could have a situation where you've got to have 95% of your residents putting in rain barrels, right? Not very practical. But these models generate results that people can use when they're having to deal with these consent order decrees. And they'll go back and forth with the state, and really it's a kind of a negotiated settlement, if you will. We need to get a much better handle on how green infrastructure affects water volume. We know from model results that in many instances it can really help out, but there's the verified data, or actual data that verifies these model results, is few and far between. And that's a real problem that we're trying to remedy. So there's a bunch of benefits. I've talked a lot about quality control and mitigation of flood risk. But there's also, I think, an economic part to this as well. This is something that EPA in Cincinnati has been looking at quite a bit, again, at a much smaller scale. But we've been looking at credits for putting in green infrastructure, whether it's in a private setting, whether it's a company or a neighborhood. We've been looking at the social acceptance of it. So there have been some non-engineering aspects to this. In other words, we went to a neighborhood. This was a study that was done about 5 years ago in a specific neighborhood just outside of Cincinnati, saying, how much would you be willing to pay for a rain barrel? That was it. It was a simple question. And once we got the data back, there was anywhere from free to you're going to have to pay me $50 to put in a rain barrel, right? So it really ran the range on the acceptance and what it would take from not only an economic but a social acceptance standpoint to implement these types of things. Now keep in mind, we're sitting here in Columbus where it's rained for a day and a half. I know in Cincinnati it's been raining for like 3 days. We also work a lot with states and cities that don't see anywhere near this kind of rainfall. And so, but when they do, it tends to be fast and furious. So there's some aspects there in drier climates that we really want to take a look at as well. And then also there's a lot of aesthetic and health benefits. A lot of these areas really do improve visually, and they're a lot more comfortable, I think, to live in. I use that term loosely. Right now in St. Louis, I was mentioning St. Louis earlier, they're under a pretty restrictive consent decree, and they put a lot of great infrastructure in the center city, and there's a lot of residents in the center city that are just howling about it because it's just plain ugly, right? And so this is another aspect, I think, that if we could get a better handle on as far as quantifying these impacts or these issues with how people react. We've tried to do this in the past with real estate data, but that's tough because there's so many other confounding factors depending on where you are. So we're trying to use a suite of indicators to say, wow, this really is raising the quality of life in this area as well as preventing stormwater from getting into surface waters. The two main focuses of our research in green infrastructure right now in stormwater management are specifically working with states. In this case, I mentioned St. Louis before. We're working very closely with St. Louis, and continuing the development of our modeling tools for stormwater management. The most prominent tool that we have that was developed by a guy named Lou Rossman in EPA about 15 years ago is the stormwater management model. And that's free open source code that anybody can get in and mess around with. It's available from the EPA website. It tends to require some background and some knowledge in stormwater management as well as knowing your way around a computer model. But a very simplified version of that, and again, I'll be blunt and open with you when it works, because we're having problems with it right now, is a program called the National Stormwater Calculator. And that actually calls on the SWIN model to predict or to give you an idea of what your stormwater rate is going to be at the scale of about 20 acres. It's not going to get you a watershed scale or a city scale, but it will get you a local scale estimate of your runoff, number one. And number two, it allows you to put green infrastructure into the model to see, hey, if I put in a rain barrel on my house, will this help? And if so, what kind of lines will we cut down? So the technical assistance, a lot of that's focusing on life cycle cost and developing, in one instance, soil quality criteria. This is a very interesting aspect, I think, from an engineering standpoint in cities. City soils are very rarely geologic soils in a classic geologic sense, so they're not layered anymore. They may have been pulled and pushed around and dumped on. You have no idea what's in the subsurface. There could be debris there from 50, 60, 80, 100 years ago. So this guidance actually tells people, tells municipalities, okay, these are the things that you need to look for if you want to take a vacant lot in Cleveland or Detroit and you want to transform that into a green infrastructure, whether it's, say, a rain garden or anything like that. These are the things that you have to look for in your soil before you put that rain garden in. This is just a summary of some of the place-based research that we've had across the country. A lot of our work has been focused in Detroit. I know this is kind of hard to see, but that has been in partnership with a lot of the work that we've done in brownfields and revitalizing urban centers. That's where all of the soil characterization work was done. That work actually applied also to New Orleans with some work that we did down there on some green infrastructure implementation. But let me tell you, the water table and the soils in Detroit are very different than they are in New Orleans. So New Orleans has a whole different set of circumstances that they need to deal with. And one of those circumstances is the water table that you hit within 2 or 3 feet in a lot of space, in a lot of places within the city. So there's not a lot of places for that water to go. So when we started looking at green infrastructure there, we realized we need to start going up rather than trying to put things on the surface. So it can be very site-specific, the implementation of these things. So I mentioned some of these models. I'd be happy to send links out. You could actually, to be honest with you, Google is much better than the internal EPA website. So Google will get you faster there than searching within the EPA website. But these are just some of the tools that we've been working on the past few years. And again, open and honest, we are facing pretty drastic budget cuts. And essentially, we are going to be really, I think, out of this list, probably focusing on maintaining the stormwater management model and maybe to a certain extent the National Stormwater Calculator. Some of these other models will probably be put on the shelf for a while. The one at the bottom that says new, thankfully, the person that worked on that got it housed outside of EPA's firewall. It's actually out of, I think it's, I want to say Catholic U out of DC, I think is the guy who worked with it on. So it's actually going through them. So that should be accessible for some time. But all these models, and I mentioned before that models are essentially what are used by municipalities to meet these consent order decrees, to talk to officials and say, yeah, well, our model is telling us we'll save 20% if we do this, 20% stormwater runoff if we do this. A lot of these models are based in some way, somehow, on the stormwater management model. So there's plenty of commercial versions of the stormwater management model out there that you can pay for that are a little slicker, have a better interface with the user. But, like I said before, it's open source code, and we aim to keep it that way. I just want to say a few words about the Office of Wastewater Management. So the way EPA is structured, we got EPA Office of Research and Development over here. We're Switzerland, we're neutral, as we're supposed to be. And then you've got the program offices, most of which are in DC. And one of those program offices is the Office of Wastewater Management. They also have a green infrastructure initiative that we work closely with them on from time to time. They've got programs such as the Campus Rainbow Design Competition, so that's an annual competition that goes out to universities. It gets students involved to put together essentially plans for a park or maybe an entire campus for managing water and beautifying that area through through green infrastructure. They also do a lot of technical assistance, and we work with them quite a bit in developing research and tools. I'm going to give you one example. We worked with a little bit on office wastewater. It's a brewery in Lancaster, Pennsylvania. And I wanted to include this slide because, not so much because of the economic stuff, but to bring up one really important point that if you're a water engineer, you don't really care about, or I shouldn't say that, you do care about it, you don't really think about it, right? And what I want to bring up here is that picture on the upper right was before they put this green infrastructure in, which consisted mainly of swales along the road, as well as a garden that they put in to surround the patio that they installed. That, of course, made the place beautiful and all that, and it really upped their revenue, particularly during the summer months. I don't know if any of you did that. It really is a really good part of Pennsylvania. It's very nice. But what I wanted to point out was the structure of the street, and this is where urban planners, I think, come in, and they always get into a room and they yell at the engineers and go, you guys don't know what you're talking about. We've got to get a fire truck around this corner, right? That's a huge issue, particularly in urban settings, right? You've got to make sure that your buses, your fire trucks, everything that a city needs to do has got to be able to do it. And engineers, I think, myself included, tend to think from time to time we're the center of the universe. And we know what's best, but we got in there and they said, absolutely not. You cannot design this the way you planned on it. You have to take into account, and in many cities, this is code. Right, there are calculations for getting a long hook and ladder fire truck around a corner. So these are some of the I think, really important points in this example where we have to work together on this. It's just not an engineering thing. It's an engineering thing. It's an economist thing. It's a social acceptance thing. It's an urban planning thing. It really does take a team of mutts, right, to put these things together. What are some future research needs? And this is just my opinion, not agency policy or whatever disclaimer I was probably supposed to read before I started talking. We still need better data on the effectiveness of these models that we use for green infrastructure. And let me define effectiveness. Water quantity, number one, volumes of water, okay? And what that's going to take, in my opinion, is picking a spot, modeling the heck out of it, using whatever model you want, come up with a range of volumes, okay, whatever, it doesn't have to be an exact number, but then go out and effectively put monitors where you need to monitor, preferably real time, and track that over the course of a year. That's it, right? That sounds easy, but these types of efforts are really hard. They're hard from a data management perspective, especially if you're picking up real-time data on flow rates and a bunch of other things, precipitation rates. Although a lot of that we can get from USGS, so there's partnering that has to go on there. But these types of studies are not easy to do, but we really, really need to do them. So we're able to go to a municipality or a state that's dealing with a combined sewer overflow issue and say, look, based on these models, which are verified, this is what you need to do to knock this down by 50% of what's going into the river. Let me also define effectiveness by saying water quality. We really don't have a good handle on how green infrastructure affects water quality. We've been doing research for the past 3 years on this, and to be honest with you, it's a mixed bag. You see some green infrastructure implementation that really does seem to take nitrogen and phosphorus levels and knock those down quite a bit. But then you see other instances where it's the exact reverse. We've seen green roofs in different environments, and depending what kind of material you use in your green roof can have a really, really big impact on the water quality coming off of that green roof. And lastly, this is what's going to tie into, I'm about on time. This is what's going to tie into the second part of my talk, if you guys are still awake, is integration with overall urban management in bold and underlines. And what I mean by that, in kind of a narrow sense, admittedly, it's not going to be a big picture talk. I'm going to talk a little bit about some of our work in urban water reuse. So when you go to a building, that building, if you think about it, produces a lot of water. On the upper left-hand part of that building, you've got black water coming from toilets, kitchen sinks, utility sinks. You also have gray water, what we call gray water, coming from clothes washers, bathtubs, and showers. having witnessed my young children in these situations, you've got precipitation coming down to the tops of these roofs, both at the rooftop and then collected at the street grade of the building. And then you've also got, in many instances, groundwater coming in from some sort that needs to be pumped out. So there's a lot of water going on around the building. And we work very closely with San Francisco Public Utilities to start developing guidance for what we call non-potable reuse. And so this would be taking, in this case, water with the exception of black water, and taking that and establishing what do we need to treat this to maintain its safety, yet reuse it. So that report just came out this year. There's a California Blue Ribbon Commission that is taking that report and trying to integrate that with new code and state level regulations for potable reuse for decentralized systems. And we want to build on that, although it's going to take some time, to start working and looking at possible potable reuse of water in decentralized systems. This term decentralized is a little bit squishy in a sense that what does that mean? Is it only buildings? Not really. We have, and the vast majority of communities in the United States are small communities and small water systems. We want to start looking at using these decentralized types of techniques and technologies and processes to start seeing if small systems can start implementing them in the U.S. I've always bristled a bit because I do a lot of work with rural water, the National Rural Water Association. The assumption on the part of a lot of engineers and people in Washington, D.C. is that, oh, they're a small system, they don't know what they're doing, there's high turnover, they'll never figure it out. But really, in the past 10 years, I've seen a huge change in both the quality of water supervisors and workers in small communities. It's not across the board, but in many instances. And also the use of technology in these small utilities. They're getting better. And so I think the time is getting right for us to start looking at these small communities that may have to deal with droughts, wildfires, less precipitation, and how they might be able to start looking at integrating stormwater as well as water reuse to augment their water sources. Why are cities interested? Well, many cities are really interested in augmenting their water supplies. You know, when you think of drought, you don't think of Atlanta. But about 6 years ago, there was a horrible drought in Atlanta. And now some of the best water reuse research is going on in Gwinnett County, right outside of Atlanta. So it really, we can't always count on this, right? 2-3 days straight of rain. Drought is going to hit at some point in different areas of the country. And cities are really keen on how do we prepare for that. Reducing potable water consumption for non-potable uses, always a good thing if we can cut down on water usage. In a way, and I'll talk about that in just a sec. Treating only what we need closer to the source, rather than having it go to wastewater treatment plants. A secondary part of high precipitation events, if they increase, and eventually sea levels coming up, where are most wastewater treatment plants? Anybody? They're at or near sea level. And we saw that with Hurricane Sandy that hit New York, New Jersey area. They were dealing with it in Cincinnati when the Ohio came up. They're at those spots because that's where you want everything to go. And so these are all issues that we're going to have to start dealing with. And can we start maybe decentralizing wastewater management as we know? Don't know yet, but that is one aspect of it. There's a lot of other benefits that cities are looking into when it comes to water reuse, and I won't read them all to you. But I will talk to you about what we're doing. And we're focusing really on decentralized research because we don't want to duplicate anything that the Water Research Foundation is doing at the big scale. So in the water world, there used to be a separate Water Reuse Research Foundation, a separate Water Environment Research Foundation, and a separate Water Research Foundation. Water reuse, wastewater, drinking water. Over the past 4 years, they have all become one. Now they are known as, I think they dropped the V, because I was always teasing them because, oh, you sound like the Ohio State University. But they became the Water Research Foundation, so it's all one. They're all under one house right now. They do a lot of work with big guys. This is an association of subscribers pay them money to fund research, and those subscribers tend to be the larger cities with the deeper pockets, not small systems. So that's where a lot of our research is focused on, is for people who may not be able to afford the membership to WRF. But we've done a lot of work with anaerobic and aerobic membrane bioreactors. These are very small footprint treatment systems. And gray water, which I'm going to talk a little bit more about in just a second. And also identifying surrogate organisms. And I know people who are maybe biologists or environmental scientists or engineers are maybe glazing over a bit here, but I'll try to walk you through this. One of the big things when we set a water standard is something that we call risk, and what's acceptable risk, and how do you calculate this risk. And let me just try to walk you through this real quick. This is a basic cartoon. The biggest thing on the left-hand side is at the bottom, this issue of tolerable risk. What does 10 to the negative 4 ppy mean? That means you're willing to tolerate one person out of 10,000 people getting sick once a year. That's your acceptable risk. And so in this quantitative microbial risk assessment approach, you establish your acceptable risk, then you go back and you say, hey, how many pathogens do we have in this water? Regardless of what type it is. It could be a stormwater, it could be a treated water, whatever. How many pathogens do we have, and what's your best estimate of a dose that person might drink? That's how we put together these quantitative microbial risk assessments. That's the basic structure of it. EPA uses typically, as for example, in drinking water, 2 liters of water per person per day. That's just standard use in regulation development, and a lot of our research, that's one of the standard issues. Pathogen density is a little tricky, and that is really where we've had to focus most of our efforts in trying to put these QMRAs together. To go out and get a consistent number of norovirus or adenovirus can be really, really tough, depending on what you're looking for. And although chemicals can be an issue in both green infrastructure settings and water reuse settings, the real driver is pathogens. In my opinion, straight up pathogens. Now, having said that, in the drinking water world, you have a little thing called public relations that you have to deal with as well. So if you go to a consumer and say, well, now you shouldn't be worried about this chemical, this perfluorinated alkyl substance in your water, because it's 20 parts per trillion, and it's well below our recommended guidelines. In the drinking water world, yet people don't want anything in their water. Okay? So drinking water is a little bit different than some of these other things. But having said that, that schematic on the left generated all those numbers in the table on the right. And essentially what that says is that for, depending on what you're looking at, let's, I don't know, just take the top gray water one, indoor use. We need to have a log removal of 6.0 of viruses to meet that 1 in 10,000 criteria, a 4.5 log removal of protozoa, or a 3.5 log removal of enteric bacteria. What is a log removal? A 1 log removal would be 99.9% of that is out. 2 log removal would be 99.99. So when you get up into log 6, 99.99999, right? The 9s keep going. And why is that? Well, it's almost entirely driven by that pathogen density. In a lot of these water sources, you've got an enormous number of these microbes or these viruses in your source water. And that's why that log removal requirement can often go out to 99.99999%, because you've got to get those organisms down to that level to meet that 1 in 10,000 criteria. So then what do engineers do? Well, when you have a log removal number, you go to the literature, and in many cases, whether it's a state or somewhere else, you can look up and see what log removal credits are given for a particular treatment technology. And that's typically what we do. But that is an active area of research as well, because technology is constantly changing. Membranes, for example, filtration apparatus are constantly getting better. And so we are on this a lot. A fundamental problem. Wait a minute. I took management training, and there's no such thing as problems, right? They're all challenges. But I'm going to go ahead and say problem anyway. A fundamental problem with technologies is state acceptance, and particularly in the drinking water world. it's really hard to get, there's National Sanitation Foundation standards for things that contact water. So if you go to Home Depot, you might see a piece of PVC pipe that says NSF on it. That's the National Sanitation Foundation. They've approved that pipe for whatever they've approved it for, maybe drinking water. But there's no broadly accepted standards across the country, and that's a real problem. And it's a problem for vendors, because if you're inventing a widget of some sort, a drinking water treatment process or technology, your requirements may be different in California as they are in Idaho or as they are in Illinois, and it's a huge hassle for vendors. They would very much like to see across-the-board standards for a lot of these things. That's sort of where this is going, but we're not there with a state acceptance yet. So when we talk about non-potable reuse, does it make a whole lot of sense to monitor Ecoli, which is an organism that is not, that's more commonly associated with black water? And we've done a lot of research that says no. Use organisms that are pertinent to the gray water that you're using. If it's a clothes washer or a shower, these almost inevitably involve some sort of organism that's associated with human skin. Almost inevitably. Why do we need that type of organism? Because if there's not enough of an organism, we can't track it, and we don't know how well a treatment system is going to work. So we've done a lot of work in this area of identifying what we call surrogate organisms to account for or estimate how good a treatment system works. And this slide back here was bacteria, and the one on the right, I know it's kind of hard to read, but the tallest one in the blue is the one that we really like to use, which is Staphylococcus. Very common organism on human skin, both in, again, laundry and showers. So we can track that organism if we're testing new technology, and if it's removing Staphylococcus, our assumption is it's removing all those other bacteria. Most of the time, that's a good assumption. Viruses are a little trickier because they're a lot smaller. And so when we're looking for a surrogate there, the one, I'm going to skip this one. These are some of the possible candidates that we've looked at. But the one that is interesting, the one at the top, quote-unquote plant virus, it turns out that there's, I gotta get the name right, here it's just referred to as PPMV. It's a pepper mottle virus. And this virus it's just loaded in wastewater. And we don't really know why. Why is this virus making it through? It's benign, it doesn't hurt anybody. But we see it at very high levels in wastewaters almost across the country. And so that's the virus that we're starting to target to use as a surrogate. Because if we see that virus being pulled out at whatever treatment we're doing or how we're monitoring it, we're pretty assured that the black jagged line that you see there, which is norovirus, which believe me is one that you don't want to get, we can be pretty sure that virus is coming out as well. This whole concept of taking green infrastructure water reuse, and using all of these as alternative water sources is a big, big deal to the Water Research Foundation. It's a big deal for EPA. It's a big deal for a lot of organizations across the country. There's a study coming out this year on alternative water source requirements for conventional drinking water treatment. What does that mean? Well, any water source that you have, whether it's reuse, whether it's green infrastructure, stormwater, whatever. These are the criteria that we need to have before it goes to our drinking water plant. They concluded that all these would work, with one exception, and that's gray water for use at a big scale, in city and municipal scales. The problems that they have with gray water, and that would be, mind you, collecting gray water, if you could do that, which is that last bullet. That's the problems. You've got to have a separate collection system and transmission system to get that gray water down to a treatment plant, some sort of treatment, so you can reuse it. That costs a lot of money, conveying systems and collection systems. But as you get to the drinking water plant, these elevated nitrogen and organic carbon levels cause a real problem for the drinking water plants. They don't recommend it at big scales. Other scales, fine. But look for that report. It's going to be really, really important. Many of you may be familiar with this. Some of you may not be. But I would urge you to, if you really want to see some ins and outs of engineering going on in urban systems, go to the Renew It website. That stands for Reinventing the Nation's Urban Water Infrastructure. This is a National Academy Science-funded center that Richard Luthi is in Stanford, as well as, I believe, it's David Sedlak at the University of Berkeley. It's very engineering. But they have looked at some other economic and social aspects. But they've been doing this for about 5 or 6 years now. They've really made a lot of hay. So I urge you, if you're interested in looking at urban water management, and rethinking urban water management, Purdue is a good place to go. Future research for us, I mentioned verifying these GMO results in real settings. I probably said that 10 times right now, so it must be pretty important to me. Characterizing and evaluating source water for fit for purpose. So I kind of walked you through some of these pathogen issues with alternative water sources, such as stormwater. One of the big challenges is, and I didn't think this was possible, we don't know much about stormwater quality, right? We don't know much about the bacteria in it. We don't know much about the viruses in it. We don't know much about how we're going to use it as alternative source water. And so we hope to fill in some of those gaps over the next couple of years. We want to continue developing these using quantitative microbial risk assessments, some of these targets for decentralized potable reuse. And we also want to start applying, as I mentioned before, some of these decentralized building schemes to smaller systems out in rural communities. And that's it. I'd be happy to address any questions, whether they can talk or not. Thank you. Really apologize for this. I felt terrible after the Overflow. Sorry.
It's only one now, rather than 50. Okay, questions?
Yes.
Please, Brett.
You talk about the uncertainty associated with green infrastructure, but it seems to me that gray infrastructure is not necessarily all that more certain. Whenever you have a natural component, you're always going to have uncertainty, including human error, that just because something's engineeringly designed well doesn't mean people are going to install it well. So it seems to me there's some issues just in terms of our reliance on what we say is certain as opposed to what truly is certain.
I would agree with that. I think perhaps I didn't mean to oversell gray infrastructure, but I would agree with that. There's going to be human error. Whenever you're putting these types of things in one particular area in Cincinnati, there were, if I remember correctly, there was an issue with a concrete cistern that they had been installed where it was cracked. They couldn't figure out why it wasn't holding the volume that it was. And once they found the problem, they, of course, fixed it. But I think to address your question, and perhaps something I didn't stress, in many instances, perhaps not all, it's probably going to behoove us to use a combination. And that, I think, is a research area in itself. How do you integrate gray and green to get the best bang for your buck? Because budgets are shrinking. And it's just across the board. That's the way it is for now. So how do we integrate these things to get the best bang for the buck? Other questions, comments? Yes?
So with that being said, or maybe you don't know it yet, but prevention versus treatment, where would you put your best dollars to get the best ROI?
Could you define prevention a little bit better?
Everything from toxic algae blooms,
Oh, right.
to volume, to dealing with the volume of water.
I didn't know how far back.
You can go to
I'm certainly not going to talk about any climate change research if you're going that far back, preventing climate change, which, by the way, we've got to do.
Well, that impacted Toledo. And it's impacting here in Central Ohio too with the algae blooms.
Yeah, and some of these discussions. First of all, yes, prevention is, and I'll give you a specific example that's not Toledo. So I'm sure most of you know about the powerful algal bloom in Lake Erie, which is almost an annual event to varying degrees, but I guess it was 3 or 4 years ago. Was it 2015, 14? 14, that's right. I just saw 5, so I don't know, 14, 15, somewhere in that range. And Toledo had shut their water down. And because they had seen microcystin, which is a algal product, a chemical that's produced by these cyanobacteria, they saw it above the limit in their water system. They shut the water down. It was over a weekend. They were helicoptering samples down to our lab. And I just said I was going to talk about this too much, but I'm going to sidetrack. But the prevention there for those types of things, we feel, are in the nutrients area, right, and reducing nutrient runoff. And I know I thought OSU was recipient on one of the sea grant funds that looked at, and it might have been you who gave the talk. It was an outstanding talk, and I'd love to follow up with you, but and if I butcher something, please stick your hand up. But one of the things that they looked at was applying their models to say, okay, we can't cut everything down in this watershed, but where do we go using these models where we know that if we cut this out of the herd, so to speak, we'll get a 40% reduction, the highest reduction for the lowest possible land area, something along those lines, correct?
Yeah.
Sweet, I got it sort of right. But let me switch that one, and I'll use another example, and it's my new favorite contaminant, that's perfluoroalkylated substances. PFAS are ubiquitous, they don't break down very well, they're water soluble, and they're in everybody in this room's blood. I can almost guarantee it. They're all over the place. And they're used anywhere from Gore-Tex fabrics to the big bad player used to be Scotch Guard fabric protector, but that's just one of many uses of these things. Wastewater treatment plants and industrial sources are pretty significant. And we think that there are certain air emissions scenarios where these compounds are emitted in the air and deposited on the soil. In fact, just up the Ohio River at Washington Works, I can't remember the town, is it Washington?
Parkersburg.
Parkersburg, thank you. Just up the road in Parkersburg, there's the Washington Works, which is a Chemours plant, and there's pretty good evidence that there's deposition, even though it's on the West Virginia side of the river, that there's significant deposition going on the Ohio side. And I'm 100% for prevention. So what does that mean in the water world? That means some form of pre-treatment, industrial pre-treatment. And can we get there? We're not going to get there yet, but that may cut down some of these sources. So yeah, I don't think you find anybody in EPA that wouldn't be against some sort of prevention in these areas. And we're working on it. The nutrient issue is a big one. I mean, it's just, and sometimes you feel kind of like, is it at Sisyphus, right? And you got to keep pushing the rock up, right? And you push the rock up and it rolls back down again. And nutrients, it just seems to have been on this for so long. Why aren't we any better? And I think it's a legitimate question. Is it that there's more of these chemicals being used? Is it population change? What is it? USDA's had a riparian buffer strip program for, God, it's got to be 50 years now. And why aren't we better? And I don't know the answer to that. Yes?
You didn't include on your list sanitary sewer overflows, SSOs.
Yes.
That's a challenge in the gray infrastructure world. Columbus has about 100 spots in their sanitary sewer where it intentionally overflows. It's designed to overflow.
Yeah, I touched a little bit on that in combined sewer overflow down in Cincinnati. We've seen multiple events where that's happened. It's invariably a high precipitation event. They literally open the gates. You go down and collect samples when they open the gates, and it goes straight into this creek that feeds into the Ohio River. The way Cincinnati has tried to deal with that is they've gone upstream on the Mill Creek, which is a pretty, it's not a huge, but it's one of the main tributaries in the city that dumps into the Ohio. They've gone up Mill Creek into that watershed and they put in temporary storage. So what it does in high precipitation events, they essentially collect all the water, stick it in these gigantic tanks, and then wait for drier days to slowly release it back into the system. A very gray approach, right? But that brings up an important point. Sometimes, in some instances, I wish there was more time to consider GI, and that's why I think having this data that we could show people and say, look, this worked in this situation. Your situation is the same. You can use it. We don't have that. We don't have those good examples. So, because of time issues and deadlines, cities go to the gray option like that. So it may not only be a control issue, it may be their only option at that point if they don't have that I don't want to say rock solid, but more solid data on how GI performs. We've also got to take a very critical look at some of the GI that we've been promoting for the past 5 years with the EPA. We're starting to get a lot of data back, for example, on permeable pavement that clogs in 2 years. Does it make a whole lot of sense to spend that much money on something that's going to clog and become regular old pavement in 2 years? We got to rethink some of these things. You know, we want to promote it as an option, but at the same time, we have to be realistic, subjective about it too, objective about it too, subjective, whichever one. Anyway, other questions, comments? Yes.
So you mentioned earlier about the need to combine gray and green infrastructure, and I just wanted to know if there was work at the EPA that you guys were doing along those lines. And in addition to the combination part, besides water, there are other pros and cons also that would come in. There may be carbon sequestration benefits, maybe air quality benefits, and so on. So are people looking at this from that bigger, more holistic perspective?
Yeah, we did some air quality benefits work, but we honestly, a lot of it was in modeling, and we just didn't see the benefits. It was in the weeds. We couldn't see it. The models that we used just didn't have the resolution for it. As far as combining green and gray, yes, and we hope to build on that in St. Louis. As I mentioned before, St. Louis is implementing, as we speak, a lot of gray infrastructure that is not very popular with people in the city. So we're looking to try to find some neighborhoods where we can get in and work with the city as well as the state to try to integrate both gray and gray. Yes?
I was just curious, you mentioned the cost of separate collection and transmission lines for, gray and potable. Do you ever think a day will come when certain communities decide that tap water is just not going to be potable, like we take for granted, like a lot of places in Europe, that the cost that if it's one or the other, we're going to just go?
I don't know.
So that would cut down on a lot of, you wouldn't have, the percent of water that we actually drink that comes out of potable lines isn't that high probably.
No, it's not. And there's a lot of people involved in research involving life cycle analysis that say, God, drinking water is going to get done the same you could ever do. Nobody drinks it, right?
Yeah.
You're washing your car with it, you're flushing your toilet with it. Does it make a whole lot of sense? So we've done a lot of work with fit for purpose water, fit for purpose consumption, kind of from a life cycle perspective. But I can tell you right now, in the water reuse world, and stormwater may be an exception, we don't know yet. But in the water reuse world, I do a lot of work in water reuse. So I'm the chairperson for the issue area team for Water Research Foundation's water reuse research. And we just had our research planning meeting a couple months ago. And over half of what we do and what people want is involved with public relations. It's come so far in 10 years. I can't tell you, specifically in areas where they've just been hammering away for 10 years, and in areas that have been dry as a bone. People all of a sudden get real religious about water, when they don't have it. And they go, yeah, well, maybe water reuse isn't that bad. But the steps in the past have really been baby steps. So you start with non-potable, and then you move on to potable. But we've learned some lessons along the way there too. Do you go to Tampa at all? Have you been to Tampa? Tampa is very famous for purple pipe. And as you drive around Tampa, you'll see purple pipe coming up out of the ground all over the place. They've invested an enormous amount of money to put in a dual conveyance system for their reused non-potable water. And it's already kind of old hat, And that's why there's such a big push right now, especially in a lot of these drier cities, to go what we call pipe to pipe. There are no pipe to pipe operations in the United States yet. They are piloting one in El Paso, Texas. And what I mean from pipe to pipe is you're going straight from what we call an advanced water treatment facility straight into distribution system. You are bypassing the drinking water plant. That is a big deal. There's one plant that does that in Namibia. That's the one that's always held up as the poster child. But this is a big step in the United States. And I can tell you right now, politically, that's what got EPA's attention. The program office. I've always been interested in this stuff, but the program office, up to that point, the regulatory part of EPA's attitude toward water reuse was, well, that's why we have drinking water regulations. Why should I worry about water reuse? Now, when they're bypassing the drinking water plant, they've changed their tune. They are starting to look much more closely at this. And I'm saying, fine, here, come to the table. So, conveyance systems and some of these aspects of using these alternative water sources, whether it's stormwater, whether it's rainwater, treated reused water, whatever. These are big issues, and we definitely learned some lessons along the way in places like Tampa. And I would argue that when it comes to water reuse, if you want to see one amazing engineering operation, just go to Singapore. They took an entire harbor, blocked it off, and pumped all the salt water out. It's insane. And it was all because they didn't want to be beholden to Malaysia for their water. And their population density is so high. They started 20 years ago on this. They said we were going to be water independent, and they are.
Okay, I'm afraid we're out of time, but thank you very much for a very interesting talk. And remember, April 17th, Bill Hunt from North Carolina State. Check CURA.osu.edu for more details. Have a good day, everyone.
And if you're an engineer and you want professional development hours, sign up sheets in the back.
Yeah, sorry, didn't mention that again. Exactly.